Hello, everyone. My name is Adewale Oladeinde, a PhD student from Portland State University. I will be presenting our work titled Image Placement Optimization in a VFED Stacked Patch Antenna for Full Duplex Wireless. This is a joint work with co-PhD student Samuel Shipe and my professors, Professor Isan Ariafar and Professor Brainomir Page Simovic. The outline of this presentation would cover an overview of full duplex communication. I'll take a minute to share with you the key motivation of this work, following which I will talk about passive self-interference cancellation, technique for full duplex wireless communication, which is a main area of this research. In discussing passive cancellation technique, I will delve into what electromagnetic band gap structure are and its implementation in this work. And furthermore, I will discuss the stacked patch antenna geometries and the EBG configuration models designed for this research. And finally, I will share some simulation results from the different model configuration of stacked patch antenna and mushroom EBG models, and then summarize with the contribution of this work. In Q1 of 2021, Ericsson reported an increasing traffic growth of data, which exceeded 66 exabytes. And this increase in data volume are mostly fueled by video content and increasing IoT devices. So in order to satisfy the hunger of higher data, wireless researchers have proposed different solutions. Some of them are moving to higher frequency with higher bandwidth, especially at millimeter wave of 28 gigahertz. Another area of research has led wireless researchers to move from half duplex to full duplex communication, also known as simultaneous transmit and receive, in order to use the existing band, especially in the sub-6 gigahertz, more efficiently by employing spectrum reuse technique. So in this research presentation, we have chosen a combination of these two techniques to enable spectrum efficient full duplex at millimeter wave. In order to better understand the full duplex communication, I would like to quickly touch on full duplex radio communication channel with emphasis on self-interference cancellation techniques. On this slide is a full duplex transceiver channel, which is presented. From the right side, we see an active full duplex cancellation technique, which comprises both analog and the digital self-interference cancellation techniques. And its cancellation techniques happens between the LNA input and ADC outputs of the transceiver channel. On the left-hand side, however, is the passive cancellation technique, which is the focus of our research. It uses structures between the TX element and the RX element to reduce surface wave from one antenna element to the other, and in order to reduce self-interference signal between these two antenna elements. And passive cancellation technique come in different techniques, which has been researched over time. Example are antenna separation, which has its limitation, especially for millimeter wave radio design. antenna polarization, the use of circulator, and use of electromagnetic band gap, which is a focus of my research. The key motivation of this research is to optimize the placement of different mushroom EBG configuration models within a TX-RX stacked patch antenna environment. So in order to achieve higher self-interference isolation, this eventually would enable full duplex communication. Another key motivation is to study the surface wave reduction between the TX and RX antenna by these mushroom EBG configuration models, which I will be talking about in my subsequent slides. So what is electromagnetic band gap structure? This slide presents what EBG is. And EBG structures are artificial, periodic, and sometimes they can be non-periodic structures that prevent the propagation of electromagnetic wave in a specified band of frequency for all incident angle and all polarization states. So EBG typically can be realized by periodic arrangements of metallic conductors in dielectric material, substrates also. And they pose high impedance property for all transverse electric and transverse magnetic polarization. The equation on the left are used to determine the EBG capacitance and inductance through the EBG patch and the shortened via sizes shown in this model, this figure. The figure on the right, however, shows the experimental analysis of mushroom EBG structure designed for 28 gigahertz operation using transmission line as the device on the test. The red line, the red curve actually show higher transmission loss resulting from a periodic structure of EBG as the reference for the device on the test. While the blue curve here, shown here, shows lower transmission loss resulting from this solid plane as the reference plane for the device on the test. So specifically for this research, we evaluated 2 stacked patch antennas, one for TX and the other one for RX, on the same substrate environment. The antenna is designed on a 4-layer stack up using Rogers material R0333, R003. The stacked patch antenna has its patch on both top layer and inner layer, as seen in this side view. And the antenna are fed, it's actually fed using microvia and grounded coplanar wave transmission line, as seen here. And it's also shown here in this figure that is spacing between the TX and RX patch antennas is designed to have 16 millimeter pitch on the same substrate design. So we further modeled 3 configurations of mushroom EBGs between the TX and the RX patch antennas and evaluated the reduction in surface wave which actually led to reduction in interference between the TX and the RX antenna elements. Figure 1 here shows what is described as the top layer mushroom EBG, because the patch of the EBG is on the top layer. And as you can see, the EBG is spread out between the TX and the RX. In figure 2, the mushroom EBG has its patch on the inner layer and is spread out between the TX and the RX. On figure 3, we have a combination of the top and an inner layer patches of the EBG, shotted with the ground VA, and is spread out between the TX and the RX. Table 1 here represents the mushroom EBG placement sizes. And as you can see, we have for the top EBG, we have the patch sizes, the EBG patch, and the EBG to antenna edge distance, the VA size that was used, and the VA drill height for corresponding EBG model configurations. So the results that we came about as a result of this different EBG configuration actually are presented in this slide. The simulation results showed a wide band stack patch antenna with 2 resonant frequency points at 28 gigahertz and at 31 gigahertz. There is a 1.7 gigahertz of bandwidth around the 28 gigahertz and an 800 megahertz around the 31 gigahertz. From this figure below, the top and inner layer EBG showed a better narrow band isolation of more than 40 dB when compared with models with no EBG. And it also has a 20 dB more isolation when compared to other EBG placement configuration models. And this table also summarizes the data shown on this plot. It is important to also note that the increase in isolation by the top and inner layer type EBG is as a result of the reduced EBG patch capacitance when 2 or more EBG patches are stacked and connected using a common shortened VS structure. The reduced capacitance, however, what it does, it further reduces or increases the high surface impedance path of the electromagnetic path from the TX to the RX. The effect of the different mushroom EBG configuration is presented in this slide. And as you can see, there is minimal effects of the mushroom EBG structures on stacked patch antenna. This is seen on the E field gain and the H plane gain. There is a 5 dB around this area of increase in back side lobe of the E plane gain, while the main lobe gain is actually consistent for both E plane and the H plane. On the other hand, there is overall gain. The overall gain versus frequency of the antenna element is consistent up to 28 gigahertz. And there is a decrease in gain performance resulting from mushroom EBG at frequencies above 28 gigahertz. That's actually the downside of actually integrating mushroom EBG in an antenna environment. There's likelihood of actually impairing the antenna performance, and it's a good thing that we have the antenna performance being consistent up to 28, and we're seeing the gradation which is less than 0.2, between 0.1 and 0.3 dB above 28 gigahertz. So lastly, in summary, we have designed a TX and RX stacked patch antenna with integrated mushroom EBG model configurations, and optimized and evaluated through ANSYS HFSS simulation. It is also noted that the top and inner layer mushroom EBG realized a higher isolation which is above 20 dB at 28 gigahertz, compared to other types of mushroom EBG configurations. There is also a greater than 40 dB of isolation when we compare this model with no EBG at all. Increasing the number of EBG patches greater than one, and with optimized placement within the TX and RX substrate environment will further reduce surface wave and increase isolation, which eventually will enable full duplex, which enables full duplex communication. And lastly, the effect of EBG on antenna performance, especially gain, is seen at 28 gigahertz frequency and above. Thank you very much for listening. I will entertain any questions. Thank you very much.